Alright, this is the last video for chapter 13. So what we've looked at so far in the previous videos is we learned about Faraday's law. Oopsies. Learned about Faraday's law. We talked about Lenz's law, which allowed us to figure out which way that induced current's going to flow. And so today we're going to look at a different kind of electric field, the one that's caused by a changing magnetic flux. And we're also going to look really quickly at generators. Just as a note, we are not going to cover eddy currents. We have to make some choices in tough times, and we just don't have time. All right, so the first thing for today is the idea of this induced electric field. So Faraday's law basically talks about an induced EMF. It's caused by a changing magnetic flux. Okay, this is the induced EMF. And just to remind you, an EMF is a voltage. So somehow we're creating a voltage. And in the previous video, we spent a lot of time trying to figure out what direction the current would flow that was caused by that induced EMF. But if you remember from previous chapters, we talked about electric fields and how they're related to voltage, etc. So it turns out that, so we have this expectation that there's a relationship between the EMF, which is a voltage, and an electric field. I hope that's not confusing because we have two E's here, but the script is different for the two. Oh my goodness, I just messed up my E. But there's a relationship between voltage and electric fields, and so it seems reasonable to think about the fact that there must be some sort of electric field, and there is, but it's important that we understand that it's a different type of electric field. This is not your beginning of the spring semester electric field that we spent a lot of time on. It is not due to some sort of charge distribution, so it's not like the electric field we looked at in Gauss's law. This electric field is caused by a changing magnetic field, and that's kind of important to remember, that it's one way that we can create an electric field. The other thing just to know is that it's not a conservative field. If you remembered, we talked about how the electric force, F equals QE, was a conservative force, and we ended up, there's a potential energy associated with electric charges, but that's not what we're talking about here. Again, it's really important that we remember that this induced electric field is different and new. Let's imagine a scenario where we could be thinking about that induced electric field. So let's say we have a solenoid. So the solenoid is like a coil of wire, looks a lot like a spring, and we're going to put a conducting loop around it. That's this right here. So you know that the whole point of a solenoid is to create a relatively uniform magnetic field down the axis of the solenoid. And so because of that, there would be a flux through our wire loop, the loop that's on the outside. Again, it's this one, the one that's on the outside of the solenoid, because, magnetic flux is B dot A. And so there's a cross-sectional area that magnetic field in the solenoid is passing through, and it's also passing through our wire loop. Now, if we create that magnetic field in the solenoid by a current that actually changes in time, then the magnetic flux is going to change. So the magnetic field due to in the solenoid can be given by this expression, B equals mu naught times N times A. But if I changes with time, B will change in time, and therefore the magnetic flux changes. in time. So what would result is that an induced current will flow in that wire loop, and right here you see that current indicated. All right, so let's look at the picture from another point of view. You know, this is looking at the solenoid from the end. And so we said that the B changes in time. And so you have a changing magnetic flux that goes through that wire loop, and that's going to cause an induced EMF. And that causes a current to flow through the loop. So there's the induced current that's flowing around in the loop. So it's going around like this. I'm going to use I prime to indicate the induced current. Okay, so let's kind of get to the point where we can say there's an electric field. So we learned in previous chapters that there could be a potential difference that was equal to the integral of E dot dl. Like if you go through an electric field in a particular distance, if you integrate across that, you're going to find a potential difference. Like if you move with the electric field, there's a potential difference. Well, in this case, we're going the whole way around the loop to get our induced EMF. And so this then represents what we call the induced electric field. Now, this field is not caused by charges, and it actually is caused by the changing magnetic field. Basically, at this point, what we're just doing is we're acknowledging that this electric field exists. When we start to study light, this relationship, the fact that a changing magnetic field can cause an electric field, is going to be important because it'll help us understand how light can travel through space, because it's going to be related. Right now, we're just sort of introducing that idea. In the end, this will leave us with a new way to write Faraday's law. And we'll just kind of leave it at that for now, and we'll come back to that in a chapter coming up really soon. Now, the one last thing that I wanted to cover was the idea of a generator. Now, a generator is a device that generates electricity. You might be familiar with that idea. If you have frequent power outages, sometimes your family might buy a generator so that you can have power when the power goes out. Interestingly, a generator will basically use what we call we'll use Faraday's law to make that current. And so the way that it works is, now of course a real generator is not going to be just one loop of wire, but here's the basic idea. If I take a loop of wire and I place it in a magnetic field, and so here the blue lines are the magnetic field lines, and what we're going to do is we're going to make that wire loop rotate around a vertical axis. Here you see its rotation, and that is going to create a changing magnetic flux. So the magnetic flux through that wire is going to be equal to the magnetic field times the area of the loop times the cosine of the angle between the area vector for the loop and the magnetic field. And here you see it labeled in this picture. However, that angle is going to change with time, and so we could actually write theta as omega times t. where it's the rotation rate. Now, if we want to look at the change in the flux with respect to time, we would take the derivative of this. Now, we're not changing the magnetic field, we're not changing the area, but we can take the derivative of the cosine with respect to time. That'll give us a negative sign, and the cosine will change to a sine, and then we take the derivative of the angle, which is going to give us a factor of omega. And so this is basically what the induced EMF is going to be. Well, I got a negative sign there. And so that is how we create a current, because a current will now start to flow in that wire because of the induced EMF. Interestingly, because of that expression for the changing flux, which was B-A omega sine of omega t, which was a negative sign, this whole thing, remember though that this is minus E, so E is B-A omega sine omega t. The EMF that's created actually changes sinusoidally with time, which also means that the current is going to be sinusoidal. And this is exactly what we mean when we talk about AC, which is alternating current. Now, in lab, you always use a power supply or a battery, and you always have direct current. The current is constant and just doesn't vary with time. But you might know that the current that you get out of a wall plug, an outlet in the wall, actually is alternating current, and it's because of the fact that this is how we generate the electricity, is through this idea that is based on Faraday's law. And that wraps up Chapter 13.